Good. Okay, hello again. How are you going? Tired? Looking forward to the barbecue? Okay, so thanks for coming back to the second lecture. So what did we see yesterday? So yesterday I finished the lecture formulating what is the distance conjecture in the Swampland program. Okay, so just to remind you, the idea is that if we have an effective field theory coupled to Einstein gravity, we have the Einstein term, and we have a bunch of scalars, no? That they are going to have some kinetic metric, okay? So this is the kinetic metric, not the space-time metric, okay? That depends on phi. If they are all, I mean, if you can diagonalize this, then this is canonically normalized, okay? The message is that if the scalar vectors of this become very large, in the sense that we are approaching an infinite distance singularity in this moduli space, in this scalar manifold, there should be an infinite tower of states whose mass behaves exponentially in terms of that geodesic distance. Okay? Since I have infinitely many states, that means that the effective field theory is going to break down, okay? Because we cannot continue having an Einstein gravity description. You can think that all of them will contribute to the graviton propagator, so that's what reduces the cutoff. If I have time, I will explain this more carefully, but yeah, the idea is that also, I mean, the cutoff, no, that we were discussing behaves exponentially, can be a different power with this distance. So the AFT breaks down at a scale which can become parametrically lower than the Planck scale if we are in these corners of the moduli space. Okay. Some of you were asking me how to understand this M0. So the point is that well, we have like the moduli space. This definition is kind of a relative thing, in the sense that we start at some given point, and then the point is that the mass there is M0. And then if we move to another point that is separated by a distance given by delta phi, then the mass here differs from the mass here by this exponential. Okay, so that's like a relative thing. In practice, sometimes it's, I mean, yesterday when I was giving you examples, I was giving you like the local result for the masses at each point. So in practice, the point is that in string theory, when we have, I don't know, different compactifications and so on, very well what's the result actually at infinite distance, and you kind of expand, like you start going. So this is sort of, you can also think of this as a perturbative expansion at the delta phi equals infinity, okay? In such a way that this is the leading term, okay? So in practice, I mean, you can also think, okay, find one of these trajectories that go to infinite distance, locally, at a point, you have that the mass of the tower goes as m Planck times a function of other scalars that remain fixed, so I'm not moving here, remain fixed. And this, the leading correction in terms of this phi is just this delta phi, or if you want, I mean, locally is the value of phi there, plus corrections. That should be subleading if this phi is very large. Okay, so that's what we obtained yesterday in all these examples. Any question? Yes?
In the case of compact space, if phi goes to negative infinity, in other words, the compact volume becomes very small. Does it mean that somehow the winding mode?
Yes, I will go. I will discuss this right now. So let me. But yes, I will explain this now. Any other question? Okay. So yeah, yesterday, I mean, we just saw two examples, like string theory in 10 dimensions, the most basic thing, let's say, like it's just one scalar. Then we also saw compactification. Then we saw that when there are two options, like when the string coupling becomes small, we have this tower are the tower of string oscillator modes. And the other example is that if the volume of a compactification becomes very large, This tower are just the Kaluza-Klein modes. Okay, nothing fancy, nothing mysterious. These examples already capture the essence of the distance conjecture, so that's why I started with that. So it's because otherwise, and if one starts with it, a bit like why this is happening, it's a bit more like magic. But of course, these are only 2 examples, so by no means they are enough to conclude anything. Okay, and the plan today is to get deeper into the landscape of string theory to perform more systematic checks of this. Okay, so today we are going to focus on, I mean, the whole day is going to, well, the whole hour, which you want more, but it's going to be about string theory compactifications to Minkowski space. So still we stay in flat space, okay? And these are going to be moduli spaces. So this is massless, okay? So they are well understood cases. And tomorrow we'll venture into the ADS. Okay, so we'll consider theories with ADS background and translate this to a CFT statement that then we can aim to prove using CFT techniques. Okay, today is flat space, so you can imagine that we are explorers in this landscape, in this jungle. We have seen this pattern in the simple examples, and now we are wondering how universal it is. Okay, so we need to get deeper into the landscape and explore, okay, step by step, how universal it is. Of course, to conclude anything about universality, we cannot just focus on the typical examples. We really need to understand the weird cases, the strange corners, uncharted territory. So it's a dangerous field. But that's what one needs to do, okay? So I'm gonna start with the example we had yesterday of type 2A on a circle, okay? We are gonna analyze it a bit more detail because indeed there's more limits than only the large volume limit that are at infinite distance, okay? And one that example is more clear and we have really understood it, I'm gonna give like a crash course, let's say, of the string landscape systematically, depending on the level of supercharges and so on, and tell you, I mean, I cannot enter in details in all of them, but tell you what is the state of the art in each case. And I hope I will have time to give you a more complicated example of, for instance, a Calabi-Yau compactifications, where we can see how this is realized, and it's not so simple as just having these Kaluza-Klein towers or these string modes. Okay? And then, as I said, tomorrow will be ADS, and the last day we'll have fun studying the Fino implications, how this can have bounds in dark photons, inflation, the size of extra dimensions, and so on. Okay, any other question? Maybe, actually, I will start here. Okay. Okay. So I'm gonna title these string dualities because by studying this example of type 2A in more detail, we are gonna recover all the most famous dualities in string theory that actually I think is useful also for the lectures of Henry, of M theory. And then we're gonna see how it seems that dualities is what is behind the existence of these towers. So let's take again type 2A string theory. Okay. Now, rather than just, I mean, yesterday I gave you the general expression of compactifying on some volume of dimension n. Okay. So just to make it simple now, let's consider compactify on a circle. Okay. So we have Minkowski 9 dimensions times a circle. That's it. And then the moduli space is 2-dimensional, right? So we had the volume, which is the radius of the circle now. So yesterday I gave you that there was here some powers in general, right? So if we are, let's make it now concrete. If we are decompactifying, if we have one compact space and 9, this is a theory in 9 dimensions. This is 9 plus 1 minus 2, 8. This is 1. Okay, it's just one circle. D minus 2, 9 minus 2, 7. Okay? So far so good. So this is the canonically normalized scalar. Okay? Yes?
Wouldn't you also have to think about like the Wilson line that comes from like grabbing the one-form field?
Yes, I'm only, sorry, should say, this is the non-compact scalars. I'm focusing all the time now on the non-compact scalar. So yeah, 2D, yeah, it's a bit, let me put it like this, 2D slice of the modular space, which is precisely the slice that is non-compact. And then in addition, yeah, you can have compact scalars, in this case like the Wilson line is compact, so it will not add new infinite distance limits. Okay, good. So non-compact scalars, we have the radius and we have the dilaton, right? So just to write again the conventions, the canonically normalized dilaton was given by log GS. Okay, we continue here. So we're interested in the infinite distance limits. Okay, so we saw yesterday, okay, when the radius of the circle becomes large, right? So rho goes to infinity. This is an infinite distance limit. Then we have the KK tower of states becoming light. I'm gonna write all the powers again because this is gonna be important today. And this is always in Planck units, okay? Sometimes the Planck, I'm just gonna write the number of the dimensions, okay? So it's like the Planck scale, 9 dimensions. Just call it M9, okay? So right now I'm gonna, since we are in 9 dimensions, we write everything in Planck, in 9-dimensional Planck units, okay? And then we had the other case we saw when the string coupling goes to 0, phi goes to infinity, right? Because there is the log behavior. And then we have the string towers, right? The string oscillator modes that also in Planck units, they go as e to the minus 1 square root of 8. So this was the result of yesterday. Minus, here I had also some n plus d minus 2, blah, blah, blah. If you replace it in this case, it's 56, okay? Okay. Now, the power of this conjecture is that this should work for any infinite distance limit of the scalar manifold. Any scalar, any infinite distance limit, okay? Doesn't matter what it is. So already here we are already missing some infinite distance limits. Some of you were remarking, which is that if the radius goes to 0, this is also, right, an infinite distance limit. Rho goes to minus infinity. Okay, so since R, the radius and GS are defined from 0 to infinity, this is defined from minus infinity to infinity, right? It's a scalar field that lives in R, right? In the compact line, in the real line. So we have the two infinite distance limits. And then, according to this, we should also have a tower of states becoming light. And now it's not the Kaluza-Klein tower, right? So what it is, indeed? What's the tower now? A winding. So if you study string theory, one of the things you learn when you compactify, right, is that you can have strings wrapping the circle and the tension, right? So the mass is gonna go the string scale square. This is the tension of the string times the radius. This is with dimensions, okay? This is dimensionful. So precisely when the radius goes to 0, they become massless. And this is the tower of states in this case of the distance conjecture. So you can try to do it as an exercise. I mean, all the time, you just need to know these two equations. So the 9-dimensional Planck scale is related to the 10D Planck scale this way with the radius, and the string scale is related this way with the Planck scale in 10 dimensions. So using these two things and the metric here, you can just write all these masses in terms of the canonically normalized fields. So in this case, the result is, believe me, but check it at home, 5 square root of 2 plus 3, actually, let's put 6 over square root of 56. Okay. So indeed, now they become light whenever rho goes to minus infinity, okay, when the radius becomes small. Good. And the other infinite distance limit that we have is gs going to infinity, right? Because that also corresponds here to phi going to minus infinity. That's also at infinite distance. And of course, any combination of these, so infinite distance, right? And then, what is the tower now? You saw it in the previous lecture, actually, right? So if we are in type 2a and the string coupling goes to infinity, I mean, it becomes very large, where are we going? M theory. And then what is the tower, the first tower of states that we find? The D0 branes. Okay, so type 2a indeed has a tower of states, which are the D0 branes. That you can also write, I mean, this is always in 9D Planck units, so using the expressions that Henry gave you also. I mean, this is the string scale over GS. So if you write it in Planck units and the canonically normalized fields, I mean, I put here, sorry, this M9 should be here because I put the scales here, okay? This is e to the square root of 9 over 8 phi minus rho over 56. Okay? Good. Now, I'm keeping the exponential rates because one of the things I want to do is to quantify, okay, what are these alphas here. And if you look at this, it seems a bit very model dependent, right? Like it seems you get random numbers, but it's not. So all these numbers we can explain, okay? So if I want to read the exponential rate, I mean, if I only had one scalar, okay? I mean, if I only had one scalar, right? This alpha is just the derivative of the mass over the mass, right? In general, we have a multidimensional moduli space. So let me define, I'm gonna call it these scaling vectors. Sometimes they are defined with this chi. So it's just the gradient of the mass over the mass, but now it's a vector because we have several directions, right? Okay. And then the exponential rate, right? Let me write it carefully, yeah. So if we are, I mean, we have, it's like, imagine that we have the modular space, right? We are in a given, we are moving in a given trajectory on the SIG. Locally, we can always compute these vectors that live in the tangent space, right? Okay, so these are like vectors. And then if I want to compute this exponential rate, what I need to do is to project these vectors over that trajectory, right? And that gives me the exponent, okay? So alpha along a given trajectory, so this alpha is going to depend on which trajectory we take, no? It's just the projection of these gradient vectors over the unit tangent vector of the geodesic. So what I want to do, I mean, now let me compute these vectors in these cases so that I can talk about the exponential rate. And we are going to see how this exponential rate is actually very constrained, okay? And it depends just on the nature of the tower. So they will all collapse to the same value. So maybe let's see if it fits here. So, I mean, in general, you can write this, I don't know, in terms of the Bilbine, if it helps. Let me put it here. So if you have a metric, right, locally, we can decompose it in terms of the Bilbine flat space, right? So this would be like the derivative with respect to phi I, and then derivative of the mass over the mass is log m, okay? But here, I mean, we don't need to get, I mean, this is just so you have the formal definition. Here, since I'm already writing everything in terms of the canonically normalized fields, I just need to compute the derivative and that's it, so because the metric is flat. So if you compute this vector for the first one, the kk, it's a two-dimensional vector who have the dilaton and the radius. So it doesn't depend on the dilaton, so it's 0. And then for the radius, it's square root of 8/7. Okay? It's clear what I'm doing, right? Now, for the string, it's 1 over square root of 8, 1 over square root of 56. So now you can see why I was writing all the, okay, the exponentials carefully. For the winding modes, we have 1 over square root of 2 and minus 1 over square root of 56. Okay, sorry, here I forgot. We define it with a minus so that we will extract the exponential rate, okay, because the tower is e to the minus alpha phi. Okay. And then for the d-zeros, it's just minus square root of 9 over 8, 1 over square root of 56. Okay? Yes?
For the winding one, why isn't it minus 6 over square root of 56?
Sorry, because I did a mistake. It was my mistake. It should be that. Very good. Thanks. Yes, the rest are fine, right? Yes. Okay. Okay, so far so good? Good. So now, let me now compute the modulus of these vectors. Okay? We know how to do this, no? So far, there is no complicated math. So, I mean, we'll get to the calabillas at the end, but the moment is easier. So, so the modulus, in this case, is easy, 8/7. Let me compute now the winding first, okay? Then we'll talk about the string. So, so now we have, do I put 1/2 plus, let's see, 6 squared over 56, which is 9/14 square root. So if you compute it and sum, 14 plus 9 over 2, you get exactly a square root of 8/7. Okay? Let's compute now the d0. Okay, so here you have 9/8 plus 1/56. So again, 7, 9, this is 8 times 7, so 9 times 7 plus 1, 8/7. Okay, what's going on? Why this is happening? Typically, we are not lucky in physics, right? So, why they all have the same value? What's your guess? There's a reason for that. this is a Kaluza-Klein tower of the compactifying one dimension, right? We go from 9 dimensions in type 2A to 10 dimensions, right? The winding modes, if you have studied T-duality, when you study string theory, actually you can see that type 2A on a circle is T-dual to type 2B on a circle, in which if the circle is small in one case, it's large in the other. So precisely the winding modes of type 2A correspond to Kaluza-Klein towers of type 2B. So the interpretation of these winding modes is also decompactifying one dimension. Okay? It's just that now we are not going to type 2A, we are decompactifying one dimension and going to type 2B. But it's the same microscopic nature. I mean, it's decompactifying one dimension. These zero branes are also decompactifying one dimension because we go from type 2A in 10 dimensions to M theory in 11 dimensions. So they are also a Kaluza-Klein tower from the M theory perspective that corresponds to the compactifying one dimension. So even if our original frame, which is type 2A, they are very different fields, they have a very different origin, there is always some duality frame in which they all look like a Kaluza-Klein tower of the compactifying one dimension. And that's why they have the same value. Okay? So in general, this alpha, like these exponential rates, only depend on the nature, the microscopic nature of the tower. Not exactly what is coming from, but what is really happening. Okay, so there is some duality frame which that corresponds to the compactifying one dimension. So they are all the same because they are all Kaluza-Klein towers decompactifying one dimension, one compact space, one-dimensional compact space, which is the circle in this case. Okay. Now, what happened with the string? Okay, I forgot the string. If you compute for the string oscillator modes, you get, well, you can also sum that, and you get 1 over square root of 7. Okay, it's different. This does not correspond in any duality frame to the compactifying one dimension. But again, if we had other towers, for instance, we will discuss it, there's also like the D1 strings and so on. If there is some duality frame in which they correspond to a fundamental string, they will also have this exponential rate. Okay, so this is also fixed. So in general, if I have in some, maybe clear, in some dual frame, okay, not necessarily the one we started with, but in some dual frame in which they are Kaluza-Klein towers, we put here a caveat. So this is when these Kaluza-Klein towers are decompactifying to a Minkowski vacuum. Okay, otherwise it can be different. Minkowski vacuum in higher dimensions. Okay. Then modulus of this vector is always given by actually the factor I gave you yesterday, which is d plus n minus 2. So d is the dimension of the space-time that we started with, n is the number of compact dimensions that we decompactify, and 2 is 2. Okay? So n compact dimensions, and d is the EFT, okay, the dimension of the EFT. Okay? So this is general. And if we have string towers, and a string tower coming from the critical fundamental string, okay, in general you can have many strings, but in string theory, but if it's a critical string, in the sense that it lives right in 10 dimensions, from a critical perturbative string, then this vector is 1 over square root of d minus 2 in general. Yes?
So didn't we say that the line was from 10 to 9 and the empirical thing was for the 11
Yes. Yeah, but because, so if I have if I start only in 10 dimension type 2A, then this 0 is going from 10 to 11 because it's the M-theory circle. Right now we are in 9 dimensions, right? Because we've already compactified type 2A. So we are going to 10 dimension because there's still the other dimension remains compact. So we are actually going to M-theory on a circle. So it's the M-theory circle. So when I say 10 to 11, I mean like the M-theory circle. But it could be that you're going from 9 to 10, which is what is happening here. Exactly. Yeah? More questions? Okay. So, yeah, and now, of course, then right, as I said here, the exponential rate, I mean, we can choose trajectories that we are only moving like only on this radius or only on the dilaton, so then this would just be the exponential rate, but we can also choose trajectories, infinite distance trajectories that are combinations of these things, and then we have to project, and this would be the exponential rate, okay? So the exponential rate is not like, I mean, what is fundamental is the modulus of this vector, okay? Then we can have different projections depending on which trajectory we are taking, okay? But then the message is just that, yeah, this, the modulus of these vectors, which are related to the exponential rate, is fixed by the microscopic nature of the tower. Okay. This is something that seems obvious now, but when this conjecture was formulated, they just said that alpha was a random parameter. Okay, so there has been a lot of work understanding this in many more complicated examples and reaching always the same conclusion. Okay, so it's like an improvement that now we understand that this alpha is not random. It's actually, it gives you information about the nature of the tower, and it's very constrained if the nature of the tower is constrained. Okay, so in particular, notice that the larger the value of alpha of the exponential rate means that the tower decays faster. Okay. So here, right, this value in general, okay, so this is the kk, this is the string, right? So this is always smaller than the one of the kk. Okay, you can compute this. Actually, you can recover the one of the string as taking n formally infinity. Okay, so it's like you can decompactify. I mean, the one that decays faster is the largest value here, which is when n is equals 1, is what we computed here. When only you decompactify one dimension. If you start decompactifying more dimensions, this value becomes smaller. And then in the formal limit in which you decompactify infinite dimension, that precisely matches with the value of the string. Okay, so the string gives you a bound, let's say, on how small this exponential rate can be. Okay. Good. Now, one more thing before finishing this example. It's not only that the nature of the tower, so let me write it clearly, nature of the tower well, determines will be like the exponential rate, okay, this is modulus of the vector. But also, it actually constrains even more things. It constrains how the vectors relate with each other when you have a given moduli space. So here we have a two-dimensional, like the non-compact part, it's a two-dimensional moduli space. We have different towers depending which direction we take. And how they relate with each other is also fixed by the nature of the tower. So what do I mean with that? So for instance, you can compute that the scalar product of these vectors, which is going to give us also the angle between the vectors, not only the length, but we are also care about the angle. In all these cases, is fixed. If you check it, I mean, carefully, by the dimension of the space-time and the number of dimensions you decompactify, so that if they are different towers, the scalar product is just 1 over d minus 2 in all the examples that are known, okay? Whenever we are talking about Kaluza-Klein towers and string towers in some frame. If it's the same tower, there is this extra factor to recover that length, okay? So 1 over d minus 2 plus 1 over n is precisely that, okay? But this is very powerful. Like if they are different, it's just fixed by the dimension of the space-time. And also, well, maybe the also I will tell you in 2 minutes. So, okay, this is the scalar product. Any question for the moment? Yes?
For the distance, is this conjecture only for string theory or for general quantum gravity?
Well, that's always coming back to the question, yeah, how general is this? So, for the moment, we are, as I said, we are explorers, so we are starting in string theory. We are learning whether this is a universal feature. So for the moment, we are going to focus on just the string landscape. Okay. Then tomorrow, we'll move to the CFT, AD-CFTs, and then we'll see that it's actually very universal for any CFT. So if you think that in holography, any CFT, like any ADS background in quantum gravity, regardless of string theory, should have a CFT dual, then you can argue that this is more general because it will work for any CFT. But it's part of the game, right? To understand how universal it is. So for the moment today, string theory. Okay?
Since when R goes to 0, there are light winding modes, does it imply that they have to?
Yes.
But for string theory, these are known facts. Why is it called conjecture?
Yeah, you're saying, let me see if I am understanding your question. So you're saying now, okay, in string theory, it seems obvious you have winding modes, so that's fine. But if this is general in quantum gravity, it seems to suggest that you need to have strings in a sense, because you need to have something that wraps the volumes and the circles so that it becomes light. So yes. So somehow, I mean, it seems that, this is telling you that, string theory is much more than that. It's not enough just to have higher spin fields. But yeah, it goes in the direction of saying that it seems that if this is a general thing of quantum gravity, something similar to string theory, right? You need to have some extended objects that wrap the volumes. And that also goes in line, I discussed the last day, like for instance, from the bootstrap. You can try to understand what is this cutoff, where Einstein gravity fails. And one of the results that is known is that, well, there are two options. Either it's some sort of Planck scale, or if this lambda is smaller than the Planck scale, this lambda, this cutoff, must be associated to higher spin gap. So it needs to contain, you need to have higher spin fields for a UV completion that is unitary and so on, that respects unitarity and causality and so on. So I think it's related. I mean, the fact that it seems that when we have weakly coupled descriptions and it's not about Planck scale, like Kaluza-Klein is more like having a cutoff related to the Planck scale, while the string towers is more related to having a cutoff associated to the higher spin gap. So whenever it's about the string towers, whenever it's, this limit seems to suggest that, the UV completion needs to have higher spin fields somehow. Yes?
Sorry, I just want to understand the statement. So if I take the dot product of the Kaluza-Klein vector and the d0.
Yeah, it's not obvious now.
There's an extra factor of 6.
An extra factor of 6?
Between the winding dot Kaluza-Klein or no?
It shouldn't. Then I did a typo when writing something. So if you this is, let me be clear. Between towers that become light along the same direction. Okay, so it's, okay. Yeah, sorry. I will make now a picture that will be more clear. But then, for instance, if you take the, like if I go to weak coupling, like this string coupling, both the KK and the string tower become light. And then you have to multiply these two, and then you get that.
And that works, yeah.
Good. Very quick. Very nice. Okay, so let me make a picture so this is more clear, okay? See, I have, how much time do I have just to calculate a bit?
A little more than a half hour.
Okay, good. So Yeah, so I was saying, so let me plot these vectors, okay? So now we have like a two-dimensional tangent space, so we can just plot these vectors, okay? Maybe, where should I do this? Yeah, I should have wrote it in the other one. Maybe come back here then. Where is the... Sure. Okay, two dimensions. Let me take this, the direction on the dilaton component, okay? And this direction along the radius, okay? So we have vectors, we have to put points. That's easy. So if you plot it, let me just to help my plot, because they should all have the same length. So they should lie in this circle. So here I have the KK tower, right? Because I only had component on the radius. If you plot the other ones, you get something like this. Okay, so this would be like the vector for the KK. This would be the vector for the, which one? This is the winding modes, right? Yes. This is the winding modes, and this is the D0 branes. Okay. I'm just plotting. Okay, these vectors there. And then I want to do several things. So first of all, you can, let's see, what do I want to do first? Let me take this color. So these vectors, okay, where the position of these towers are actually marking the interfaces between the different duality frames. So this is like, okay, the positions. So one vector is here, here, and here, okay? So, and here I'm missing the string tower, sorry. So the string tower is somewhere, it's here. Okay, some here, yes. And then, okay. So this is the KK, this is the winding, this is the D0, and this is the string. I did this circle because I know that these three have the same exponential rate, the modulus, right? So this would be in this circle with radius square root of 8/7. The string has a smaller value, okay? But if you compute it, it's precisely on the line joining these 2 points. That's why I draw this line. And this line is nothing but the convex hull. So you know when you have points and you're a child and they tell you to join the points. So that's what I'm doing here. You can draw the convex hull of these points, which is this triangle, okay? Here. Ugh, it's messing up. I hope you do a better job than me. Okay, so I have this triangle, is the convex hull. The convex hull is useful because, as we said, the larger the exponential rate, the tower becomes faster. So if you're interested in the leaning tower, so the first one you find, the lightest one, it's like you have to check what is the convex hull. So what are the points that are farther away? Okay, so if I now move in some random trajectory, so in this plane, any of these straight lines is a geodesic going to infinite distance. So if I move in any random trajectory, I can just, like if I move in this trajectory, for instance, I will delete it now. The exponential rate, you can see, okay, here, the exponential rate is projecting these vectors over this line. That gives me the alpha. So whenever it's a positive value, it means that these towers become light, while these ones become heavy if I move in this direction. So here is like a graphical representation in which you can easily check what is the leading tower for any general trajectory and what is the exponential rate. You can just compute it geometrically. Okay. Now, maybe before I continue with the duality frames, the dot product I put there is precisely constraining the angles between these towers. Okay, so in this case, we also have here we have another tower, so here we have another duality chamber. So this angle is fixed by that, this angle is fixed by that, this angle is fixed by that, this angle is fixed by that. Okay, so that means that the natures of the towers also give information about how different duality frames fit together in the moduli space. Because if I need to complete the full picture and the angles are fixed, there are not so many combinations I can make. Okay. So coming back to the duality frame, so let's be clear. So here, when I go to large volume and small dilaton, G is going to 0. This is what was described by type 2A, okay, on the circle. And it's precisely the two towers that become light are the string tower and the Carusa-Klein tower. If I go to this part of the moduli space in which the radius becomes smaller, okay, now I have to perform a T-duality, and this is described by type 2B on S1. Okay, so it's the T-dual version. So it has exactly the same form. It's like a copy of these two things. It's just that here are winding from the perspective of type 2A, but it would be KK towers from the perspective of type 2B. Okay, so it's like you can divide your whole moduli space. So this is like a picture of the whole moduli space in this case. We could divide it in different regions, and in each region, the theory, the action is better described by a different duality frame, right? So here is, like type 2A supergravity on the circle. This is type 2B. If you go to this part, this is the region in which the radius is still large, but the dilaton becomes strongly coupled, okay? Because we are going to phi to minus infinity. So this is the region described by M theory on a torus, okay, like on two cycles. And indeed, you can see that here, this region, the towers that become light in this region are Keki towers, both of them. Like this is a Keki tower, and the D0 brains was also a Keki tower. So here there's no string, right? So even if you didn't know, of course, all these dualities are very well known from many years ago, right? This is the beginning of string theory 50 years ago. But even if you didn't know that, just by taking the distance conjecture and the towers, you can reproduce all these string dualities. And you can say, okay, here, I know that because of what is the value of these exponential rates, the length of these vectors, I need to go to a theory that does not contain strings, because here there's no string tower, but has 2 dimensions more, because this is a decompactifying 1 dimension, and this is decompactifying another dimension. So it's a theory in 11 dimensions. Okay? So that's the information you can already extract here. And then there is also this part that I didn't discuss so far. Okay? So this is the regime in which the volume becomes small for type 2A, and also the dilaton is strongly coupled. So we can access in different ways. Like, for instance, we can come this way. So here, since the volume was small, we had to perform a T-duality, right? So T-duality is here. Maybe I should write in white. So in the T-duality, right, the radius goes as alpha prime over the radius. Right? That's why you invert it. Here, okay, what is happening is that this type 2B is becoming strongly coupled. So what happens when type 2B becomes strongly coupled? What is the description then? Type 2B, but as S-dual description, right? So I was writing in blue, but yeah, this is, you perform an S-duality, and you get an S-dual description of type 2B. So this line is like an S-duality. Okay. And then there's a tower I didn't write because it's not so obvious to see from the type 2A perspective. You can see it, but which is precisely the mirror of this one. So when you're in type 2B, the fundamental string of this type 2B, okay, from the perspective of the original Type-2B, is the D1 string, right? It's the S-dual version. So as an exercise, you can also compute the mass for the D1 string in string theory of this Type-2B dual to the Type-2A, and you will see that the point precisely lies here. So here we have our, sorry, I should have put this here. We actually have another frame. So this is the S-dual Type-2B. And here we do another T-duality. It's like the same line. This would be a straight line, which is like a S-dual Type-2A. That indeed you go to strong coupling and you come back to M theory. And these two Type-2As are related just by a transformation on the torus here. So you can map the full space of dualities, and then indeed, like the existence, like this, the distance conjecture is just telling us that whenever we go to infinite distance limits, like there is some tower of states becoming light, and they are the protagonists in the sense that they are telling us what is the duality frame, no? That we are, that is better describing that theory. And then if we change, we might have another tower because there is a different duality frame that takes over, and so on. So it's one of the fundamental things of string theory that we cannot have a single description for the full space, right? Like we always have patches. And which one we have depends precisely on which towers are becoming light. So that's why sometimes the distance conjecture, I mean, some people, for instance, prefers to call it like the duality conjecture because it's really linked to the existence of dualities. Okay? Questions? Yes?
So now I'm a bit confused about this last remark.
Yes.
Does it mean that they become light along the same?
Yes, so I mean, so here, would be nice to have more colors, but so for example, if I move one direction like this, okay? These two towers are becoming light because if I project it, this is a positive value for alpha.
Okay.
But these ones are heavy, are actually becoming infinitely heavy because you project it. Oh, actually, sorry, I should have checked. Thank you. Maybe too late, but if you move in this direction, right? This projects here, so this is the exponential rate for the string. This would be the exponential rate for the winding tower, so these are light. But this one, right, this one projects to a negative value, so then it's the opposite, like there's no exponential of minus alpha, but plus alpha. So when I mean they become light, I mean, yeah, you have to check the angles between this and this one that are both light, or this and this one that are both light in this direction, or this and this one, this and this and this. So consecutive towers, in the sense.
They have to span some cone.
Exactly. They are spanning one cone, which is precisely a given duality frame. So the generators of that cone satisfy that dot product. Yes?
And so how do we know that all the points lie on this triangle? Do we deduce it from something?
So you could also have things inside, which will never be like leading towers, in the sense that there will be always another one that decays faster. So whatever is inside is heavier, okay? And you have in fact, like for instance, I can have extended objects, other things that also maybe become light, but at a slower rate, so they are much heavier, and they will be inside. So this is giving us the leading towers, the lightest ones, okay? Which is what also has information about the type of duality frame. You cannot have things outside. If you have something outside, is that you miss something, no? Because that's the lightest one, okay? So that's why we plot the convex Hall. And then you can play many games, like you can now consider more complicated compactifications and try to do similar pictures. And then you get different polytopes that are like a representation of the duality frames that you have in that compactification. And they are constrained. You cannot, it's like you can try to play to see which ones are possible or not, and then compare with examples, and then learn about how different dualities can fit together. Now, in general, I mean, here, I picked this example especially simple also because here, because of the level of supersymmetry, I know the metric everywhere, so I'm not missing anything here. And also, this slice is flat in the sense that I can just canonically normalize these fields, and this description is valid everywhere. Okay. More generally, you could have compactifications in which that metric is not flat. I mean, you can always make it flat locally, but not globally. Okay. In which case, you might not be able to have like a global picture, but you can have patches. Okay, so within each duality frame, you can always do it. And then how to glue the different duality frames, you have to take into account that curvature, which is less trivial, but yeah, it's like a technical complication. Okay. Okay, questions? Yes.
Is that one between DCO and the KK, just like the string and UI?
Say again, hi.
That one more half between DCO and KK.
No, so here, you only have bound states of these two. I mean, you can have bound states. In fact, like if you move here in the middle, like you decompactify both dimensions at the same rate, you have like Kaluza-Klein states of decompactifying 2 dimensions, and you can check that this value is precisely what corresponds to decompactifying 2 dimensions. But it's like a bound state of these two. There is no, I mean, there are no fundamentally new states. Okay? Yeah, so that's why this is just one duality frame, which is M theory on the torus. Okay. So in the last 15 minutes, right, probably, let me, not sure I will be able to do the Calavilla example, but let me at least give you more intuition about the full landscape. Okay, so we describe now completely the moduli space. This is actually the only moduli space in 9 dimensions with 32 supercharges that can arise from string theory. So that's like classification of the full moduli space. But now you can ask, okay, what about the rest? Okay, so let me make a crash course here. String landscape, again, to Minkowski compactifications, okay? Let's focus on that. Meaning that we are putting string theory in a background, which is Minkowski space in d dimensions times some compact space. Okay, so they said one can do some systematic, or aim to do some systematic classification in terms of the level of supersymmetry. So if we have 32 supercharges, this is maximal supergravity, maximal supersymmetry. These are, this compactification, I mean, this can be derived from toroidal compactifications of M theory. So you can see that here, right, even if we start in type 2A, you could say, I mean, this moduli space is described by M theory on a torus, because I have the 2 cycles. So you can also continue adding circles, like a toroidal compactification, and the toroidal compactification does not break supersymmetry. So that's why you keep the same supercharges. Okay? So you'll have 32 supercharges, but you can have lower dimensional effective field theories. These, I mean, M theory compactifications are, yeah, they all have maximal supersymmetry, and that's the full landscape. Okay, this is like a classification of the landscape for the 32 supercharges. The distance conjecture here works the same way. Okay, I can start adding more cycles, but it's like now this picture has more dimensions, but it's the same story. You have Kaluza-Klein, you have strings in different corners, different duality frames, all the things that I've said is preserved. Okay, nothing new. And actually here there were some papers proving that indeed, like that all the towers of states that you have they solve with some duality frame in which they look like this. Okay. So that's done. Let's go down. 16 supercharges. Okay. So now the story is more interesting. When we reduce supersymmetry, things get more interesting. So typical examples, which are not complete, is taking also toroidal compactifications of heterotic. Okay, heterotic in 10 dimensions has 16 supercharges, right? So you start from that, and then you have toroidal compactification, and that already gives you, many new modular spaces. How do I write this? So maybe let me just quickly give you examples. So, in 10 dimensions, the full landscape, there are just two options. Depends on what is the gauge group. It's heterotic, it's just 32, or 8 cross 8. Okay. Just some comments that I made yesterday. From canceling anomalies, there are other two groups that would be possible, but that's it. Like just anomaly cancellation already constrains a lot the possible supergravities that you can have. And then there are arguments based on not only supersymmetry, but also canceling global symmetries that rule out the other two, and they never appear in string theory. So if we are in the string landscape, these are the only two options that we know.
You can rule the other two out just from
supersymmetry. Yeah, that's why I say either supersymmetry or the no global symmetries. In 9 dimensions, supersymmetry is not enough to rule out everything. But here, like for instance, we have 4 disconnected components of the modular space. That are classified depending on the rank of the gauge group. So we have rank 17, 9, 1, and 1 we have it twice. Okay. Actually, maybe I should say, okay, this is just, let me just say it with words. Recently, it was also shown that this one also have another copy in terms of a discrete theta angle, but in terms of the low energy spectrum, that is what we are considering now, is the same, so it doesn't truly matter. So low energy spectrum, there are just 4 disconnected components of the modular space. This comes from toroidal compactifications of heterotic. This, which you could think of M theory on a cylinder. This is M theory on a Mobius string. This funny thing that's, and this is M theory on a Klein water. Okay, so these are the 3 spaces, 3 supergravities that are, that are known, arising from the string landscape. And you can do the same type of pictures. These ones we have studied in some papers, and everything works. There's a subtlety, if I had time I would discuss, but I put here, this is the value of a Kaluza-Klein towers when they compactify into a Minkowski vacuum, okay? Here already, you can already get limits that do not compactify to a Minkowski vacuum, so you get a different value of the exponential rate of the KK towers. They are non-BPS, and they go they compactify to what is called type 1 prime. The string theory, you have type 1 prime, and this has like a Romas mass, and it's like a cosmological solution. There is no vacuum. And then the exponential rate changes, just for you to know. But anyway, you can check everything, and it's always anyway satisfied. Even if the exponential rate changes, it never becomes lower than this one. So you always get that the exponential rate of the tower, there is always some tower with an alpha bigger or equal than 1 over the square root of d minus 2. Okay. Also here, didn't say, but a way to check that is that you can always have here inside of these polytopes a ball of radius 1 over the square root of d minus 2 that always fits inside of these convex holes, and tells you that in any direction there is always a tower of states that decay at least with this exponential rate. So it gives you a bound on how fast they have to decay. Okay, so here this is also satisfied. Well, don't have much time, so here story gets more complicated already. Well, 8 dimensions still are like toroidal compactifications of this, but if we go to 7 or so on, there are more components that appear, more ranks that come from asymmetric orbifors and so on. But still here you can try to have some sort of, I don't know, people are working on having like full classifications because this you can study from the worksheet perspective. And you can try to complete that. And so far there are no surprises with respect to the distance conjecture. Okay? So let's go to lower supersymmetry. That's dual. So this is like a part of the modular space is described by heterotic, then another part is described by type 1 in the same way that here you have dualities between M theory and type 2. Exactly. So it's not giving you a new component. So let me go now to H supercharges. See if I have time to say a bit. So here we have, I don't think we have like a full classification from string theory. That's hard. The known examples, right? Typically, I mean, like canonical examples always involve compactifications in Calabi-Yau threefolds. H supercharges, the maximum dimension we can have is in 60, okay? We are in Minkowski compactifications. So it's either 60, 50, or 40, I mean, or lower. But in general, I stop here because below gravity is more tricky. So here's the 16 equals 1, 15 equals 1, 14 equals 2. So this comes from F theory on the Calabi-Yau threefold, M theory on the Calabi-Yau threefold, M theory, this, M theory, and type 2. And this, okay, so this would be 14 equals 2. And here, the distance conjecture has been studied a lot. Okay, actually, this is the space in which has been more explored. I don't know why we actually started here rather than up. Like the papers that we study these are more recent than the papers that we study Calabi-Yau threefolds. And the thing is that it's very nice, like here, it gets more complicated, but you can translate the distance conjecture to some geometric properties of these Calabi-Yaus, and then prove it in general for any Calabi-Yau. So here, for instance, I mean, we have some, if we focus on the vector multiplet, so when we have H supercharges, we can have hypermultiplets or vector multiplets. So you focus on the scalars in the vector multiplets. Yeah, we can have like a proof, the distance conjecture, based on the geometry of these Calabi-Yaus and the physics of BP states. So maybe, I mean, let me, even if I don't have much time, just to give you a flavor, okay, of this to finish the lecture. So, I mean, this vector multiplet space, I mean, the metric, okay, for these scalars in the vector multiplets. Okay, let me focus on this. So the metric, I was calling it Gij. It's a complex metric. This is a complex modular space, which is scalar, which means that the metric, you can derive it from a Kähler potential. Probably Liam discussed this last week, I imagine. This scalar potential, let me be in the case of type 2A, for example, just because we were doing it before. You can write in terms of the scalars. So the scalars are these T's here, okay? And these are what are called intersection numbers of the Calabi-Yau. So these are intersection numbers between the different two cycles. So these scalars are parameterizing the volume of two cycles. Okay, so these scalars are volumes of two cycles, okay? These are intersection numbers and so on. And then you can have different infinite distance limits that you can classify depending on the value of these intersection numbers. Okay, so you can have a full classification. And the towers of states that become light now are D0 and D2 branes. Okay, wrapping these cycles, these two cycles. You also have Kaluza-Klein towers of these two cycles, but they're actually heavier. Okay, when I move to infinite distance limits of this Calabi-Yau. So the lightest ones are these two branes. Okay. And this happens, I mean, that's why these Calabi-Yaus, I mean, we're very interested, that's why we were checking Calabi-Yaus first, probably because it was less trivial that the distance conjecture was satisfied, because the lightest towers are not like vanilla Kaluza-Klein states, they always come from wrapping branes. Okay, and then you can ask, okay, do I always have an infinite number of these? I mean, these wrapping branes give me an infinite number of states. That's non-trivial, and it really relates to the physics of, in this case, of PP states in the modular space and so on. So here you can show that precisely, I mean, if you go to a singularity at field distance, you only have finite number of these, but if you go to infinite distance, one can prove that you get an infinite number of wrapping branes. Like, they really count as infinitely many states that are weakly coupled. And then the masses, like for instance, let me give you one example. So you can take, for example, if I have some singularity in which this is the volume, this is the overall volume of the Calabi-Yau. So what is inside of the Keller potential? So if the volume scales as t squared for some scalar times a function of others, okay, of the other scalars, this is a type of singularity called type 3 in mathematics. No, there's a lot of mathematics here. And then the mass of the D2 and D0, you can show that they scale actually at the same rate with this, which goes as 1 over t. So if you compute this vector that I was computing there, right, the modulus of this vector here, you get that it's 1. And 1 is precisely the value. So we are in 4 dimensions. So if I replace a 2 for n, so I decompactify 2 dimensions, so 4 plus 2 minus 2 times 2, 2 minus 4 minus 2, 2, 4 over 4, 1. So this is precisely the value of decompactifying 2 dimensions. So I'm going to 60, and indeed this is a limit that is known. This is an F-theory limit. So you go to F-theory, grows 2 dimensions, you go to F-theory in 60, and yeah, and everything works. So there is some duality frame, which is now this F-theory frame, even if we started with type 2A on the Calabi-Yau threefold, in which the tower that were coming from D2 and D0s behaves as a Kaluza-Klein tower of decompactifying 2 dimensions. Okay, and how this happens, I mean, it's less trivial. Okay, that's in the typical cases. So you can have a lot of fun with these things. Check many of these. You always have to check what are the dualities that you have, and this seems satisfied in all the cases. Okay. In the end, there is always a duality frame, which there is this description. I could also go to 4 n equals 1. That also works, but I mean, maybe ask me later because we don't have more time. And yeah, so that's the, I mean, if you want to take home message, is that so far the state of the art is that in Minkowski compactifications, this is the summary. Okay. So tomorrow we'll see whether this still works in ADS-CFT. And then the last day we'll see how these particular bounds you can now have sharp implications in phenomenology. Okay, because now you have concrete numbers. Okay, thank you. I guess we go to the barbecue, no? I don't know if...
Yeah, so the barbecue is at 6, so maybe hang out here for a little bit. The room is UNC 235. Am I writing big enough? It'd be embarrassing if I wasn't. So if you sort of walk past the Alfred Packard Grill, like turn the corner, there's these big stairs come to it from other ways. And if you look